Okay, let's talk about 70. So they give you a continuous decay rate of 27%, an initial dose of 85. So now we know there's like these two different rates, these two different percentages, percent rates, or percent change that we have. We have the true percent change and the continuous percent change, and so you have to read problems carefully to know which one, if you're given one of those, to know which one you have. So 27%, is that the actual percent change per, what is this, hours? Per hour. Is that the actual percent change per hour? No, it's a continuous rate. So remember we said continuous rate is similar to an APR. It doesn't give the true percent change per hour. Instead, you think about that as it has to be combined with the idea of continuous growth or decay to get the true percent change. Okay? So if they want us to define this function, say a of t, then which form are we able to write down right away, given the information that we have? So here are our two forms. So they gave us the continuous decay rate, so that's going to be this form. And so how does that translate? 27% tells us what about this form? Our initial dose is 85. That's easy, just 85. E to the, question is, what's going to go here? All right, he wants negative 0.27. People are nodding. That's right, because it's decay. K is negative, and we need it as a decimal. Still didn't leave enough room. Okay, so there's the function. 85 e to the negative 0.27t. Okay, and so how could we then find the true percent decrease per hour? The true percent decrease per hour is a matter of finding what? Well, we said it's not going down 27% every hour. It's something a little different than that. How can we know for sure? So how it's going down? How much per hour?
The value of e to the negative 0.27.
Okay, which represents what?
The 1 hour growth factor or decay factor.
1 hour, the true 1 hour decay factor.
Yeah, it's B. So this won't give us a rate, but it'll give us the true 1 hour decay factor. Okay, this is the value of B. B equals e to the k, right? Right here. Those are equal. So the true percent decrease comes from the true decay factor. So we do it B, and so e to the negative 0.27 is? Thank you. 0.763, which means a decrease of 76.3% per hour. Right? Nope. That's what remains. Remember, decay factors represent what you keep, what remains. Therefore, percent decrease. True percent decrease. 1 minus that, or 100 minus 76.3. 23.7. So a 27% continuous decay rate means a true percent decrease every hour of 23.7%. Okay? So that they didn't ask for that, but that's an important thing to work through, understand, be able to do. Okay? So then part B says, how long until 45 remains in the patient's bloodstream? So 45 milligrams. Input or output of this? Amount is output. Amount of the drug is output. So it's going to be 45 equals 85 So we could do either way. We could write it this way and solve for t, or we've got b now, so let's just use that, 0.763, because that is e to the minus 0.27 to the t. So if you do this, it's the exact same thing, because that part right there is the 0.763. Okay, so then we do 45 divided by 85 equals 0.763 to the t. And this is the number of hours that will get us down to 45 milligrams remaining. Okay, how do we find out what t is? It's an exponent. Therefore, it's a log. Hopefully, you just didn't all find all of your brain on break, okay? T is an exponent, therefore it's a log. Which exponent is it? The exponent of 0.763. That gives 45 over 85. Natural log of both sides. It's like your little security blanket, right? Okay, but I just saved you a step. Understand what a log is, and you can do it faster, much more efficiently. Okay. Log of both sides is just turn off your brain, follow this thing that you used to know. But we want to really practice what do logs mean, so that when you see a log, you can just know what it is, right? Rather than, oh, it's something to do with exponents, right? It has to do with solving for exponents. No, logs are exponents. And you read them left to right. The exponent of 0.763, that gives this, whatever this number is. Okay. So then the question is, this isn't natural log and it's not common log. So for a calculator, then you got to pick one of those. So we'll do natural log. Natural log of this, 45 over 85. This is our change of base formula. Remember I showed you that? ln of 0.763. You can change the base to anything you want as long as it's the same in the numerator and the denominator. Okay, Matt, you got that?
2.35.
That whole thing is 2.35? Okay. Anybody else got that? Cool. So what were we finding? We were finding a number of hours, right? It was the exponent of 0.763 that gave 45 over 85, and that exponent was the number of hours to reach 45 milligrams. Question?
Would it be wrong if you were to just use the 85 e to the negative 0.27 and did it using natural logs?
No, not at all. Okay, so you're saying that you divided by 85, and then you said this exponent is the natural log of 0.45. Yeah, should get the same thing. So negative 0.27 t, that's the exponent of e, so it's a natural log. Yeah, totally. It's good. Then we wouldn't need to change the base formula. So that's actually kind of nice. So by doing it in this form, your exponent is this, and that exponent is an exponent of e, so it's a natural log. That's what natural logs are. They're exponents of e. Natural logs are exponents of e. Other questions on 70? So 1.2, same. It's the same progression here. All right, 78. Okay, you got a city's population in 2003, and then over the next 7 years, it increased by 2.1% per year. Is 2.1%, is that the true amount of percent increase per year? Is it the true amount of percent increase per year? People are saying no. The population increased by 2.1% per year. It's telling you the population increased that much every year. It's not saying it's a continuous rate. It never says it's a continuous rate. It's telling you how much the population increased every year. This is the true rate. This is not continuous rate. So you got to just read what it says. If it's a continuous rate, it'll tell you it's a continuous rate. Here it's telling you this is how much the population increases every year. So what does that give us in order to set up a function? Is it k? No, it's not k, but from it we can get b. b equals? So this is like the first thing we did in this module, like 2 weeks ago. Given the percent increase, we can write the actual growth factor, and so then the function is? Okay. So now we want to rewrite the function in this form. So we know that a stays the same, the exponent t is the same. So what's left? E to the k. So we have the growth factor and we need k. So 1.021 equals e to the k. We just write down what k is. What is k? 0.021. 0.021? No. K is the exponent of e that gives 1.021. Therefore it is natural log, right? Exponents of e are natural logs. If you're still not sure about it, then say the exponent of e that gives 1.021. And exponent log base e, those are natural logs. Exponents of e are natural logs. Exponents of e's are that's what natural logs are. They're exponents of e. They're exponents of e. In this case, which exponent of e is it? The one that gives 1.021. Therefore, it's the natural log of 1.021. Tell me what that is.
0.0207.
78, I think,
Yeah.
if I remember. Okay. So what is the continuous rate? What's the continuous rate? 2.078%. A little bit different, right? A little bit different than the actual percent increase. This is the continuous rate, or k as a percent. All right, so what's the value of k represent? It represents the continuous rate, or the rate that when combined with continuous compounding gives us the true percent increase of 2.1%. All right, don't worry about D. We didn't really talk about that. Okay, but this stuff that I'm doing right here, it's always is really low success on the exams. I'm just trying to keep warning you about that. So if you forgot it, study it again. Make sure you study before the exam. But this difference between the true rate of increase and the continuous rate of increase and how it plays out in the functions and the equations. It's, for some reason, does not stick easily with students. So fair warning, okay? Any questions? Okay, let's go on.
So unless the question specifically states that it's a continuous.
That's right. Right. And also, I mean, you have two clues here. It doesn't say continuous rate, and it says the population increased by this much per year. It's telling you what it's doing. It's telling you the true rate. Yeah. So you had two clues. All right. So remember early in the course, and we've kind of talked about this a few times, that pre-calculus is a course about covariation. So what is covariation? What does that mean? Just have an idea of what that means. It's not on your computer screen. Trust me.
Two numbers varying side by side.
Two numbers varying side by side. Brandon, what do you think about that?
Two different amounts that vary in some sort of relation to each other.
Yeah, so and when we say, what do we call amounts? Or not amounts, but what do we call these things that are varying? Okay, variables represent quantities. Remember, quantities are measurable characteristics of objects, and we assign variables to those to take on their values. And so, yeah, so we're looking at two different quantities varying together. That's the idea of covariation. How do they vary together? So we say how two quantities change together, right? And we've looked at some different types of covariation so far this semester. So we didn't spend much time, but we mentioned proportionality. And with proportionality, you have the two quantities, their values are always in a constant ratio. Okay? So the value of one quantity is represented by y, value of another quantity represented by x. As those change together, that y over x will maintain a constant ratio. So now we've looked at two other types of covariation pretty intensely. What was the first one we looked at? Okay, and what, yeah, so linear. What do we call linear? What's that? Constant rate of change, right? So what maintained a constant ratio with constant rate of change? Yeah, what ratio was constant when we talked about constant rate of change? Anybody learn anything this semester? That's kind of like this, though. That's y over x. Is it the same as proportionality? Is it y over x? Is that what maintains a constant ratio? Change in y over change in x. Remember this? Change in y over change in x. That's constant rate of change. Y over x can be violated. We talked about that. Remember the soldier lowering the flag? We looked at y over x. We said, oh, it's changing. But still, the height versus time was maintaining constant rate of change because the change in y over the change in x maintained a constant ratio. All right, and then we came up with this linear equation. Based on that, we said that the new y equals the old y. I totally have this backwards. So we said the new y equaled the old y plus what? The change in y. And we found the change in y by k delta x. And that's how we built the equation of a line. We built it up that way. Starting from a point, we said we could look at the change in x minus a, and then we got the corresponding change in y, which was the constant rate times the change in x, and then we added the old y to get the new y, and that built every point on the line. Okay? What other type of covariation have we investigated? What's that?
Exponential.
Hopefully we're all thinking that. Exponential, right? We just spent 2 or 3 weeks on it. Exponential. And what maintains a constant ratio in exponential growth? So what maintains a constant ratio in exponential growth?
Percent change.
Okay, percent change is maintained. So what's the constant ratio? What's that? You got it. Someone got it. The next output and the current output, right? That's our growth factor, B. Right? That's our growth factor, B. So remember we said that exponential growth doesn't mean just growing super fast. It also doesn't mean just any curve. It's a very, very, very specific type of growth where the new output in a ratio with the old output maintains this constant ratio, and that's our growth factor. Okay? So exponential growth is a very specific kind of growth that doesn't necessarily mean super fast growth. It could be very, very, very slow growth, right? Okay, and then our equation, y equals a b to the x. So here's kind of been our journey on covariation. We're looking at different kinds of covariation. So in Module 5, we're going to start off by looking at covariation more generically. We're not going to look for a little bit here, we're not going to look at a specific type, but we're just going to talk about how quantities vary together and how that results in a graph. Okay, so how do we model the covariation of any two quantities? Okay, whether it's constant rate of change, exponential, or something else. Okay, this is how we do it. There's 3 steps we want to look at. The first is to identify which quantity is going to be independent and which is dependent. So we usually use x to be our independent quantity, and we usually use the horizontal axis for that. And then we usually call our dependent quantity y, and we use the vertical axis. But we could switch all those things and it wouldn't be wrong, right? This is just more convention, right? But anyway, so we got to identify which is kind of the starting quantity, and then which one depends on that quantity. Okay? And then here's what we're going to do. We're going to consider small equal increases of that independent quantity, the x quantity, and we're going to consider them one at a time. And for each increment of x, we're going to answer 3 questions. So we're going to look at these small changes in x, and we're going to then investigate what happens with y. What happens with y? So the first question we're going to ask is, as x increases by these small amounts, just simply what does y do? Does it increase? Does it decrease? Does it increase a lot? Does it increase a little? Okay? So that's easy first question. All right, but the second question is more important, and it takes more thinking. Okay? Second question is, as x increases, how does the current change in y from the current change in x compare to the previous change in y? In other words, how does the change in y change? How is the change in y changing from each little change in x from one to the next? Okay, and then just naturally out of that comes the question, how does the rate of change of y change? So we talked about constant rate of change. Now we're going to investigate situations where potentially that rate of change will change. It won't be constant. Okay? And so this is how we do that. You look at small equal changes of x, and you're basically comparing the resulting changes in y one to the next. And that's how you can make a conclusion about how the rate of change is changing. Okay, so another process here that does not stick easily. I hope everyone's taking notes. You're not going to remember this. Write it down, and we're gonna practice this, and you're not just going to remember this, because probably most of you have never done anything like this before. Okay, so write it down or watch the video and then write it down. Take notes and watch the video. Okay, so the first example we're going to look at is on page 183. So as your people are writing, go ahead and flip open to page 183. Okay, we're going to do number 1 together, and we're going to apply this thing that I just. So it says, examine the given bottle below and imagine the bottle filling with water. Make a possible rough sketch of the graph of the height of the water in the bottle as a function of the volume of water in the bottle. Okay, so first question we ask is, what's the independent quantity and what's the dependent quantity? So we want the height of water in the bottle as a function of the volume of water in the bottle. What's the independent quantity in this case? Volume, right? Remember we said this language, A is a function of B, means A is which? The output or the input? A is a function of B. A is output or input? Output. That's like the dependent quantity. So what's coming out of our function? Dependent on input. So A is a function of B. Is B output or input? Input, right? Okay, so we've got the height as a function of volume. So volume is our input or our independent quantity, and that they've labeled the axis for you there. As I can. Okay, and then so then the dependent quantity is like our output. It's like our y-axis. That's the height of water in the bottle. Okay, so independence volume of water, dependence height of the water, and then what do we do next? We consider, what did we say? Small equal increases in what? Okay, which would be in this case? Volume, okay? So we're going to look at small, like maybe we think of an ounce or a milliliter at a time. And we're going to add to this bottle. So we can say that these grid lines are our small equal increments. We don't necessarily have to have numbers here. Like I said, you could have an ounce, it could be a half an ounce, it could be 2 ounces, it could be 10 milliliters, whatever, okay? But small equal increments. All right? And then, so we're going to add our first small increment of water. Say it's an ounce. We put in an ounce, and we ask, what happens to the height of water in the bottle? It goes up. Goes up a little bit or a lot? Goes up a little bit. Okay, so here's this initial change in x right there. So there's our change in x. And we get some corresponding change in y. And then those two things taken together give us a new point on the graph. So when the volume was 0, what's the height? 0, so we forgot, so we could start with that point. When the volume is 0, the height is clearly 0. And so now we've got a first change in x and a corresponding change in y right there. You said that was a little change, a little increase in height. I agree. And that gives us a new point, a new corresponding amount of volume and height. All right, so we can't do the next step because we don't have anything to compare it to. So what do we do next? Next, change in x. So we can draw it like this. So starting at that point that we just drew, we get the next change in x. And we're going to have a corresponding change in y. Is that corresponding change in y going to be positive or negative? What's the height going to do in that next change in x? It's going to increase, right? All right, so now the question is, now we get to our second question in the 3. How does that change in y compare to the previous change in y? So this change in height, will it be greater than, the same, or less than the previous change in height? A little bit bigger. Why? The bottle's getting narrower. So the same amount of water is going to make that height go up, but not only go up, a little bit more than how it went up the first time. So then what does that look like? Maybe like this. A little bit bigger of a change than this one, giving us another new point on the graph. Okay, do it again. So here, the temptation will be to generalize too quickly. So what we want to do is really practice this, what we call incremental thinking. Incremental thinking. One little change of x at a time. And don't generalize. Don't generalize. That will be the very strong temptation, is to do like this, go this far and be like, I know what it'll be like. Okay? But we want to practice this thing called incremental thinking. So we got the next change in x. And we say, when we change x that much, what will happen to the height? Up, down, or stay the same? Up. Then we say, okay, the amount that it goes up, how does it compare to the previous amount that it went up? More, the same, or less? A little bit more because the bottle's still getting narrower. So maybe this. A little bit more than the previous change in y. Gives us a new point. One more time. Same change in x, whatever, our 1 ounce. Will the height of water go up, stay the same, or go down? It will go up. That amount that it goes up, that change in y, how will it compare to the previous change in y? Still more, because the bottle's still getting narrower. Okay. Is this constant rate of change? So what about this? So what's happening to the changes? 1, 2, we're up to the fourth one. So delta y4, how does it compare to delta y3? Greater. And how's that compare to delta y2? So the changes in y are getting greater and greater. But what was constant rate of change? Constant rate of change says for equal changes in x, we should have consistent changes in y. Well, they're not consistent. The change in y is getting greater each time. So we don't have constant rate of change, therefore it does not graph as a line, right? And we see that happening here. So as we keep putting water in the bottle, we see this graph emerging. Imagine pouring water into the bottle and the height's coming up. And that results in the points on the graph emerging, and it's not going to be a line, rather it's going to be curved up. We call this concave up. Or curved up. Concave up or curved up. And this means the rate of change is doing what? Increasing, staying the same, or decreasing? Rate of change is increasing because the changes are increasing. So the rate of change, analyzing the rate of change comes right out of this question of analyzing the individual changes. If the individual changes are increasing for the same delta x, then the rate of change is increasing. So when the graph curves up, that means your changes are increasing, and so your rate of change is increasing. Okay, so now I'll turn the tables here. I'm going to give you a graph, and you're going to do the same analysis. So do the same analysis on the graph. Look at equal changes in x, and analyze the changes in y, and then analyze the rate of change, and you're going to draw the bottle. Okay, so I'm going to give you the graph, and you're going to do the same kind of approach of looking at changes, comparing changes, and then from that, draw the bottle. So let's see how I can do here. Do this. Good start. Oh, these are the best lines I've drawn all day. Okay, so you've got 3 parts to this bottle. Here's number 1. Here's number 2. And here's number 3. So I know it's excruciating and painful, but don't just finish this in a minute. Practice this idea of a change in x, corresponding change in y. A change in x, corresponding change in y. Ask yourself, how does y change for each change in x? And then, how does the current change in y compare to the previous change in y? And you're going to do that in 3 different parts of the bottle. Okay? So I know that it seems like overkill, but it's for most of you, this is a new thing that you're doing. You've never done this before. So practice that. Don't just draw the bottle. Some of you think you can just draw the bottle, okay? And maybe you can. But practice this incremental thinking, okay? While I take attendance. So Jerome can come around and help you. So yeah, get a partner, talk it out, okay? Okay, let's see here. Okay, Britton, you're up. All right, we're going to regroup here. Let's see how you did. So, Britton, talk to me about the first part of the bottle.
First part of the ball is going to be, it's not going to be really curved, but it's going to be wide. It's gonna
No, I want to hear about changes in X and changes in Y. Can you talk to me about changes in X and changes in Y in the first part of the bottle?
So a change in X is going to correspond to a change in Y.
Okay, so I'm going to go do a little change in X here. And you're telling me that I'm going to get a change in Y. Is that an increase, decrease, or the same? Increase. And then for the next change in X,
It's going to be,
what's that?
it's going to be an equal change in Y.
Equal change in Y. And then the next change of X gives, again? So I've got changes in X resulting in a consistent change in Y. What do we got? Constant rate of change. Equal changes in X resulting in consistent change in Y. Therefore, the graph is linear. Okay, so the bottle. So if we have the same change in Y for every little amount of volume that we put in, what will the volume look like? Lexi? Yeah, what will the bottle look like then? So like the sides, will they be flared out? Will they be straight? Will they be tilted in? What's that? A little bit tilted in. This. Agree with that? Straight up? Yeah, so the way that you'll get the same change in height for the same change in volume is if your cross section stays the same, or your sides of your bottle are vertical. Okay, next part of the bottle. Elon.
We have another constant rate of change,
Okay.
but it's steeper, so we're looking at a straight ball size, but closer together.
Okay, so talk to me about changes in Y and changes in X. So I'm going to do a change in X here. What happens?
Y
Goes up. And then we do another change in X.
it'll go up essentially.
It'll go up the same amount that it did before. How do these amounts, though, compare to the amounts of change in this part of the bottle?
Change in Y is a lot greater.
A lot greater. But within that part of the bottle, the changes in Y are staying the same, right? Okay, so then what does that mean for the bottle? If so, we have another constant rate of change. We still have consistent changes in Y, but those consistent changes in Y are a lot bigger than the previous part of the bottle. So, conclusion about the bottle.
So the bottle gets thinner.
Thinner. So how does it get thinner from going from section 1 to section 2? Does it flare in like this?
No, it just goes straight.
Right, so like immediately it's thinner. So as soon as we hit section 2, all of a sudden that rate of change is less, or greater, sorry, the constant rate of change is greater suddenly. And so, but then it's constant again, so it must be that the bottle is suddenly narrower. Does it make sense? Okay, let's see. Who's next? How about Joshua up there? Third part of the bottle. Talk to me about changes in y, changes in x, and changes in y. So change, okay, so goes up. So here's my first change in x. And I get, in this third part, I get, say, change in y1. And do another change in x. And what will happen to the height of water? Increase, decrease, or stay the same? The height of the water. So the height of the water goes down for this change in x? What's that? Yeah, what? So, for this change in x, will the height of water increase, stay the same, or decrease? Increase. The amount of increase, how does it compare to the previous amount of increase? More, the same, or less? This much. How does delta y2 compare to delta y1? It's less. So the height is increasing, but the change in height decreased. So they're positive changes, but they're positive changes that are decreasing. Okay? Change in x3. We get another change in height. Is that change in height positive, negative, or the same, or zero? Positive. The height's still going up. But how does this third change in height compare to the previous change in height? It's getting less. Okay, so what does this mean for the bottle? So here we've got the changes are, what are the changes doing? Increasing, staying the same, or decreasing? The changes are decreasing. Okay? So that means for the same amount of water that you're putting in, the height, it's increasing, but at a smaller and smaller value. What does it mean for the bottle? Getting narrower? Getting wider? Okay, so this is so if you come to my office hours and you're talking to me, do you want me to stand up and walk away? Okay. Concave down means the rate of change is decreasing. Okay, so we're going to have, it'll be mostly written homework until we get to Module 7. We'll be back on web work in Module 7, so we'll have written homework, and then I'll post your quiz for Friday. We'll have the next set of quizzes for Friday and Monday. Okay, see you Friday.